Hello everyone, my name is Aditya and I study at IIIT Sri City in the computer science branch. And in today's lecture, we are going to continue the topic of equilibrium. In the last lecture, we had started this topic and we had completed a few questions from these topics. And just a quick revision of most of the questions that we had actually covered last time. So, suppose we have a reaction that is like A plus B. Just a minute, I'm so sorry for this. Yeah. Suppose we have a reaction that is A plus B gives rise to C plus D. So now what happens is initially we just have a lot of reactants, and then what happens, the reaction starts and eventually we start going in the forward direction. When do we go? Until and unless we have the concentration of products equal to the concentration of reactants. Now the concentration of products must be equal to the concentration of reactants at equilibrium, and there we get a constant which is basically called K, which is actually nothing but our product by our reactants, right? So that means that for our equation, that is going to actually be C D divided by A B. Now again, we assume most of the gases only over here. We do not assume any of the solids into this primary equation. And another thing that we studied, that suppose if I have some reaction A, B, and its constant is K. So then when I reverse it, then what happens is this becomes dA, and the constant of this reaction, let's call K dash, that will actually become 1 by K. Okay. Another thing that you have to remember is, suppose I have A gives rise to B, and then let's say I increase the thing. So I tell 2A gives rise to 2B. So then what happens if this is, let's say, K, so K dash will actually be equal to K square. Okay. So this was another thing that we performed, and finally we had solved a question that was basically delta G is equal to delta G naught plus RT ln Q. Now, just another quick revision on what was Q. So let's say at T equal to 0, our reaction started. That is basically A gives rise to B. Now, eventually we start, and at T equal to T, let's say we reached equilibrium. So we are at equilibrium here. A gives rise to B. So now for this particular part, when we are not at equilibrium, this same constant that we calculate is all referred to as Q. And at equilibrium, it particularly becomes your K. Okay. And after this, once you have attained equilibrium, you can also lose your equilibrium. Let's see. Let's say that once what happens is we start with this reaction, we have products. Okay. So we have reactants greater than products. Then what happens is reactants can become equal to product. Then there can be a time when reactants become less than product. Now our reaction or our situation at will always favor this. So if we are over here, we'd want to go in this direction, and if we are over here, we'd want to go in this direction. So this would be a forward direction reaction then, because you are forming products, and this would be a backward direction reaction then, because you are forming your reactants. Okay. Anyways, so coming back to this equation, now I hope what's Q and everything. And particularly this equation, we also solved some questions seeing that at particularly equilibrium, our delta G becomes 0. So then we just get a delta G naught is equal to minus RT ln Q. Because we are at equilibrium particularly. So this is not going to be Q, RT ln K. Okay. So more or less, this was a gist of what we had done in the last class. And we had completed around 17 questions in the last class. And we are going to start from question number 18 in this particular class. Okay. Right. So now what we have is we have this reaction BaO2 solid gives rise to 2BaO, which is also a solid, and plus O2. Now the delta H of this reaction is positive. This is a description that's given to us. In equilibrium condition, the pressure of O2 is dependent on. So basically what happens is initially, let's say at T equal to 0, we will just have BaO2. Eventually we go, we reach equilibrium. So at equilibrium, we start getting a reaction that is 2BaO2 gives rise to 2BaO, that is solid, plus, just a minute, yeah, solid plus that gives me an O2 gas. Okay, and delta H of this reaction is positive. This basically means that this particular reaction of ours, this reaction is an endothermic reaction. Okay, so endothermic reaction meaning that this reaction, and when it starts absorbing heat over here. Okay, it starts absorbing heat. Now they are telling the pressure of O2 is dependent on what? Okay, so we know that if we see the equilibrium constant Kp, now P is for pressure, so it'll be just O2. Okay, because this is a solid and even this is a solid, so we will not include these. We will only include gases or solutions, right? So partial pressure of O2 just depends on K. And now what does K depend on? K will depend on the temperature, right? So K will depend on the temperature. Kp will be equal to O2. So just O2 is technically dependent only on the temperature of the equilibrium, which should be your option C. Very simple question, nothing we did. We just saw at equilibrium whatever it is dependent on, and over there, here the production of O2 depends on. Another thing that is given to us was this reaction was endothermic, and at equilibrium, this was the only thing affecting the constant. The constant is dependent only on the temperature. So overall, you can see that the most important thing over here is temperature. Temperature. Temperature seems to be important. And that is what we are basically telling, that it depends on the temperature of the equilibrium. All right. Okay. Now let's come to question number 19. Again, a basic fundamental question of something that we have already done. Okay. So the question says that if a value of an equilibrium constant at a particular reaction is given to be this, all right, at equilibrium, the system will contain more reactants, more products, equal number of reactants and products, and all the reactants and products. Okay. Now here's the thing. We know that K is what? K is product by reactants, right? Now, if we see, all right, if we have equal number of equal products or similar number of products, okay, so there will be three classes in this, right? Technically, if our, I'm going to just refer to this as P, the products, and the reactants as R. So if my reactants is greater than my R, sorry, reactants is greater than my product, technically this thing will be a bit closer to zero. Closer to zero. K is closer to zero. Now, second question, reactant condition is reactants are equal to products. That means K is actually closer to 1 at that point, right? And second one, if my reactants is less than my product, then you can technically think of it like K will actually be very high. K will be high, right? Logically speaking, this is from maths what we can derive using this formula over here. Now look at our equilibrium constant. It is actually 1.6 into 10 power 12. Now 1.6 into 10 power 12 is actually a huge number. Huge number. And if we just see what we derived in this particular part, then, okay, So there we can see that this falls in this condition of where reactants is very less than the product. So our system will actually just contain mostly products at that point, and that is what is going to be your particular option over here. Okay, so the same thing we have actually just given it as a detailed solution over here. It's actually just the same thing what I've just told. So okay, now coming to this question. Okay, this is a two-step reaction. So first what happens is first this part of the reaction happens and then this part of the reaction happens. So this is one and this is two, right? So step one and two are favored by. So you have to see what prefers step one, what prefers step two, and what prefers step three. So we have the detailed solution of this. Now I'm going to explain this all along the way what happens. So here's the thing. Okay, just listen this out. So step one, you can see is this part of the reaction, right? And they have told me that this is a exothermic reaction. So I'm just going to write over here that delta H is actually less than zero, negative. Okay. Now, if it is an exothermic reaction, just think about this like this. Okay. I have A plus B gives rise to C. C is an exothermic reaction, meaning that this will give out a lot of energy like this, right? And if C is giving out a lot of energy in an exothermic reaction, the surroundings should be at a comparatively low energy form so that it can absorb that energy. Correct? Think of it this way. So now if you see, if it's an exothermic reaction, this side of the product side, this should be on a low temperature side. Does that make sense? Low temperature side. And because both the reactions are actually exothermic, this should happen in both the particular cases, right? That you have a particular low temperature. Okay. So now let us think about this like this. Okay. So here you had one, but you're forming three moles. So you can see the number of moles, it is increasing, correct? For every 1 mole of A and every 1 mole of B, you're getting 3 moles of C, which is still a lot. Okay, if you see the product reactant side has 2 and the product side has 3, that is still a lot. Now, if number of moles are increasing, there is a low temperature. To maintain that side over there, we actually need a low pressure, right? So then for this particular part of this reaction, we will need a low temperature. Sorry, low temperature and low pressure. Let me show you why. So you have PV is equal to nRT and this is low. Okay. This is actually increasing. This is constant. This is constant. Now to make sure that this is staying equal, you need to make sure this will reduce, right? That is what's happening over here. That is why in step one, we are telling we need low temperature. I'll write LT and low pressure. Now let's see the second reaction. Now here you can see the number of moles is reducing, right? Number of moles is reducing. Now if number of moles is reducing, even this is reducing, to maintain the equality, P should be a bit high, right? And that is why this part of the reaction in step 2, we need a low temperature and a high pressure. Okay. So I hope that solution was clear. So you can see we need low pressure, low temperature, high pressure, low temperature. That is option D. Okay. So I hope that this was a pretty simple understanding that you people got. Nothing much. I'll just explain the entire thing to you once again. So I have a reaction A2 plus B2 that gives rise to 3C. Okay. So it's a two-step reaction, right? Let me explain it on the blackboard. So I have A2 plus B2 that gives me 3C. Okay. My second reaction is that 3C gives me D. I'm working on two reactions. Now, both these reactions are actually exothermic reactions. Okay, these reactions are exothermic. Now, I told you that for exothermic reaction, we actually need a low temperature on the product side so that this whole thing goes in the forward direction, right? And what was the logic? Just look at the logic again. We have A plus B that will actually gives rise to C. And let's say that delta H of this is negative, meaning it is an exothermic reaction. So what I'm telling is, at this point, there is a lot of energy that will be released, heat energy, you can say, that is actually going to be released. So the surrounding must have a very low temperature so that it can absorb that thing. Okay, so let me write it as heat energy is released. As heat energy is released, surrounding must be at a low temperature to absorb the released heat. To absorb that released heat. Okay. So now the thing is, here we have a low temperature, and this is case true in both the cases. So over in this region, we will actually have a low temperature, and similarly in this region also we will have a low temperature. Okay. Now the talk comes about pressure. Now see, we have our standard equation, which is actually PV is equal to nRT, right? And let's say R is constant. In this case, V will also be constant. So technically, what I'll say is P is proportional to NT. Okay. And let's just make that a particular constant over here. So P is equal to, let's say, some alpha NT. Now, temperature is low in both the cases. So now if you can see, P is proportional. Let's say this is low, right? And let's assume that for now, other than temperature, then P is proportional to some beta times N. Beta times N. Okay. Now look at this. Here you have 2 moles on the reactant side. Here you have 3. Okay, let's write it here. 3 moles. On the reactant side, on this equation, again you have 3 moles. And here you have 1 mole. So here you can see that N increases, and for this reaction, N decreases, right? So accordingly, now to make sure that this is low, that is becoming high. So this thing will have to become low so that the temperature remains low, right? And similarly, over here, you have N, which is actually becoming less. Pressure should technically become less, but because you have a low temperature over here, you can technically say that to make sure that the temperature is also low and low to maintain this equality, the pressure increases. Therefore, in reaction 1, we have low temperature and low pressure. And in reaction 2, we have low temperature and high pressure. Okay. So I hope this makes a bit of sense to you what we have written over here for this question. And let's continue with this. Okay. So now we have is an equilibrium constant for a given reaction. A gives 2A is 500 Kelvin. So this is one reaction. Let's call this R1. And at 700 Kelvin, it is this and this respectively. So now what is happening over here? So if we see, the equilibrium constant would just be this, right? So now what they are telling, the reaction is exothermic, slow, endothermic, or fast. So now over here we have actually two constants, right? 1 into 10 power minus 10 and 1 into 10 power minus 5. Now that is because one is at 500 Kelvin, one is at 700 Kelvin. So what is happening is you have A2 that gives rise to 2A. I'll explain it here. So you have this C reaction, right? Okay. Now you have one at 500 Kelvin, you have one at 700 Kelvin. Now at 500 Kelvin, it was actually 10 power minus 10, and at 10 power minus 5. So now if you see, this is actually coming closer and closer to 1, right? So this is, let's say, the entire timeline. This is Let's keep 1 and 0 and huge number. So I'll just say this is n. So now over here we saw that this will be at equilibrium. This is when reactants are more than product, and this side of the thing, and in this side of the thing we saw that reactants are less than products. This makes some sense. Now what happens is, if we technically think about it, these things are very low still, right? They are very small. Now because they are very small, we can say that we still have a lot of this is lot of A2 is present. Now, because a lot of A2 is particularly present over here, I can still say that even though there is 200 Kelvin temperature increase, the reaction is still going at a very slow rate, right? It is still going at a very slow rate because the products are not yet formed to that extent that our constant is has a high value. Got it? So I'll say that this reaction is slow. Coming to question number 22. So standard Gibbs free energy for the isomerization is given to be this at temperature this. The more trans is added, then what happens? So you have a reaction that is cis to pentene gives rise to trans to pentene, right? So now what you have is you have your reaction delta G is equal to delta G naught plus RT ln Q, right? Because we know that this G is actually related to Gibbs energy, right? Now you have a temperature T, they have given you the value of R, you have to just see that what happens at equilibrium. So it is a very logical thing, right? So if you add more, this particular thing will increase. Now we are at equilibrium, so it'll just go back and it'll have to form a bit more this. Makes sense, right? So what happens at equilibrium? We know that at equilibrium, our product should be equal to our reactants that are present over there. And now if you increase the products, the reaction will go back in the backward direction. That is what I discussed at the start of the class also with you people. So now if our reaction is going in the backward direction, that means simply more of cis 2 pentene will be formed, and if more of cis 2 pentene is formed, then that is going to be our option. Okay, so this is just a detailed explanation of what we told. Now, according to Lee-Chartlier's principle, adding heat to a solid liquid equilibrium will cause the temperature to increase, the temperature to decrease, the amount of liquid to decrease, the amount of solid to decrease. So solid to liquid is an endothermic process. Now, why is this an endothermic process? You can see that there is a change of state, right? Now, we know that from change of state depends on mobility. Now, if the mobility increases, there is a lot of energy that is absorbed to increase that mobility. And in this case, the mobility changes, right? So that is why it is an endothermic process. Now, simply what happens is you are telling that you are adding heat at equilibrium. So now what you're telling is, now what you're telling, once you started this, you're adding heat, and because you are adding heat, it is already an endothermic process, more energy will be absorbed, right? So as it is an endothermic process, an endothermic process, as it is an endothermic process, we providing more heat will favor this situation. I think more heat will favor this situation. Hence, more liquid will be formed. That is what they are telling over here. More liquid will be formed, right? So we can see that using this, the amount of solid decreases. Okay. Logical question, that's very logical. Okay. So now let's come to the pH calculations. So if you people know that what is the formula of pH and what exactly is pH. So let's discuss about that a bit. Okay. So, excuse me. Yeah. Right. Now, pH is basically we are trying to measure, pH measures how acidic our solution is. Like our solution is. Okay. Now you know that pH lies on this scale of 0 to 14, and we have a middle number that is 7. So now what happens is at 7, pH equal to 7 is considered to be neutral, right? And less than 7, this side, this is actually acidic in nature. And the more you go towards 0, the acidity increases. So acidity increases as we go towards 0. And on the other hand, if we see this side, it is basic. And basicity increases as we move towards 14. As we move towards 14, the basicity increases. Now, if we talk about this, we have a thing of POH and pH. So pH measures the hydronium ions that are present over there, right? Hydronium ions means our H plus or our H3O plus ions. That is what pH measures. On the other hand, we have POH, and POH measures automatically the basicity. Okay, so POH basically just is related around our OH minus ions. Now, now, you can see that you have pH, you have POH, and technically, if you see pH plus POH should give me 14 because this covers the basic side. You can say this covers the acidic side. So, if you're seeing from an acid perspective, POH's pH would give this. If you're seeing from POH perspective, this thing would have been completely flipped, right? That is it. So that means your pH plus POH should actually be equal to 14. Okay. So this is one of an important relation that we want. Our second relation is how would we calculate this pH or how would we calculate this OH, right? So what basically is this pH is nothing but minus log of all the hydronium ions that we have. Or many places you will actually see H3O plus also. So let's just say this. And now seeing this formula, you can also tell that POH is just going to be minus log of OH minus ions. Okay. So this is a quick revision you can say that we have on pH and POH. Now you have molarity, you have pH, they are telling pH, and you have a base. You can see a base, right? Now, if you have a base, you actually can't calculate pH because you will get the concentration of OH minus ions, right? So, if you get the concentration of OH minus ions, what you'll get is you will get POH. And then using this relation, you can calculate the pH. Now, obviously, we can see it this way that it cannot be 2 because that would be acidic, and this is a basic thing we know from our knowledge. So now I hope you got the entire calculation part. So this is the calculation. This your concentration is 0.01. That means this is your OH concentration. So log this. Now log is actually over here on base 10. Okay. So the log that we take is actually base 10 OH minus ions. OH minus. Now, over here, we note that this is a simple log property that we have applied that the power comes out. So, minus 2 log 10, 10. And we know when your base and your this part becomes equal, this whole thing will actually become equal to 1. Minus into minus is actually 2. So, if our POH is 2, pH will actually be 14 minus POH, and that is going to be 12. So we can see that it is actually a very highly basic solution, that is 12. Okay, a very simple calculation of POH again over here. Let's see the next question. Which of these cannot act as a Bronsted acid and a particular Bronsted base? So now what we saw is we have seen pH, we have seen POH. Now what we want is we want to see what is a Bronsted acid and what is a Bronsted base, right? So what happens is we have acid, right? We have an acid. Let's see this. We have an acid and we have a base. Now, what Bronsted told was, what this sir told us, the Bronsted sir, was that an acid is a Bronsted acid if it donates H plus. So our Bronsted acid donates H plus, and the person who accepts this H plus is our Bronsted base. So this guy accepts the H plus. Okay. So we have our Bronsted acid which donates the H plus. We have our Bronsted base which accepts the H plus, and then this is what is our entire concept of Bronsted acid and Bronsted base. Now you have four options. You have to see what donates H plus, right? Or what accepts H plus. Now what? Now they are asking which cannot act as both at the same time. Now we know that ammonia can actually become NH2 minus, NH2 minus, and also NH4 plus. So it is acting. Likewise, HCO3 and HSO3, but HCl, it always gives H plus. It never accepts H plus. HCl never accepts H plus. Now, because HCl never accepts H plus, it will never act as a Bronsted base. And that is why HCl is the correct answer for this question. Okay. All right. So now you have to see, you have four reactions. Okay. So following solutions were prepared by mixing volumes of Ml and NH4. So they have given how much volume and how much molarity of HCl you have mixed with how much volume and how much molarity of NaOH. Now you have to see pH of which will be equal to 1. Okay. So what happens is basically what you have to overall do is here you have to compute how many molecular equivalents you have in each case. Okay, let me explain it. So suppose we take the option which they have explained, this one. All right, let me just explain what they have explained. I will. So here, if you do whatever is the volume into the molarity, okay, so you know molarity is actually equal to number of moles divided by volume in liter. Okay. Now what happens is just assume, okay, now that if we are talking in ml and we will not get number of moles, we will actually get the number of equivalents. So now what I will do is I will get my number of equivalents to be equal to volume into molarity. So my number of equivalents for HCl will be my volume into my molarity into 1. Okay. 1 comes here because, just a minute, and you have 5 molecular equivalents of NaOH. Now, how many? Only 15 of them can react with Na. Out of 15, only 5 will react with NaOH5 to make it 0. We will still be left with 10 in our resulting solution, right? So now molarity of H plus in the resulting solution will actually be 10 equivalents that are left divided by 75 plus 25, which is our total volume that was left over there in that case. And now then you just have a simple pH calculation. Just a minute, guys. There's someone on the door. All right. Sorry for the inconvenience. So I was just telling that You got 15 moles of 15 equivalents of HCl, you got 5 equivalents of NaOH. React, you will have 10 equivalents left. Then you have to calculate the molarity of that solution. Now that is the 10 equivalents that are left divided by what was the initial volume, that is 75 plus 25. So that would give me 1 by 10. Then this is our simple pH calculation from the formula, and then that gives us 1. So you have to technically just see that in each case which comes 1, and then you have to compute it. So that option C is coming, the reaction C is becoming that particular reaction. So C is your correct answer. Okay. Okay. Next, what is the pH of the resulting solution when equal volumes of NU zero point 0.1 molar and point this is increased? So now it is actually the same thing what we were doing. First, we are calculating the equivalence. Then we are seeing that once we have calculated the equivalence of NaOH and HCl, we are seeing that the equivalence of NaOH is actually equal, very much greater than the equivalence of NaOH. Sorry, the other way around. Equivalence of NaOH is greater than the equivalence of HCl. Now, because the equivalence NaOH is more, we can say that the resulting solution is just going to be basic over here. And because our resulting solution is basic, the resulting solution is basic. So then what happens is we come to this particular equation. Now, once we solve this particular equation, we have to just find the resulting, we have to just technically solve this equation, and then we will get this particular final value, which is going to be our final concentration, and we are just going to solve it. Okay. So now what I want to just cover is that what is this particular formula that we are solving over here, right? This particular formula, if you see, it comes from stoichiometry formula, and we will come on this later. But initially, what is this? This is one, this is a second solution, and you are seeing that initially we have this solution, and then this is the resulting solution that we have over there. Okay. So, what this solution is telling that, look, you have an acidic solution. This comes under the titrations things, if you remember. And that's not the spelling of titration, but I hope you get the idea. So, you have an acidic solution. Okay. Over here, you have a basic solution. Now, what happens is sometimes they react, and you will be left with a final solution. Okay, in this case, that is exactly the same thing that has happened. We are left with the final solution that is present over there. Now, what happens is in the last question also we had the similar situation, but in the last question we actually knew the volumes and we knew the molarity, so we could have computed that. But in this case, we don't know the volume exactly. A final hard end value is not given to it, right? So that case, we will tell that initially, whatever is the equivalence of this and whatever is the equivalence of this, finally that should be equal to the equivalence of this. Okay, that is exactly what we even did here, right? You saw that initially you had 15 equivalents of HCl, and then you had 5 equivalents of NaOH, and that gave you 10, which was the equivalence of the final thing. We did the exact same thing over here also. So now what happens is you did M1V1, which is the equivalence of the acidic part or the basic part, whichever is the dominating part. And then for the basic part, you did M2V2. And eventually you got MV, right? V final. Now what in this question they have told is you've mixed equal volumes of this. Now because you mixed equal volumes, V1 will be equal to V2 and that will be equal to V final. And therefore, you can just say technically M1 minus M2, I'll take V common, is actually going to give me MV. Now, M is molarity over here. So you have the gram equivalence of this particular part, which is basically what? Your molarity into your volume only. So that part only, right? This would be 0.1 minus 0.01, and that would be the molarity of this given solution. Okay. So now that you have the molarity of that given solution, you have to just, you're done with it. Okay, that's it. You will just get the molarity of the given solution, and then you will just do it here. Now, why did we do 2v? Because look, we are adding v of this, the final solution will have 2v of it, right? So this will be 2, 2, 2, and then this will be 0.09 divided by 2. That will be molarity. Okay. So now you have the molarity of your final solution. Now that means you have your concentration of OH. Why OH? Because our solution was a basic solution, right? So you got concentration of OH minus ions, and then you have to just perform the simple calculations that we have already learned, and you will finally get the pH value. Okay. So in this case, it's option A. I hope this basic thing is clear to you. Now, which of the following salts will give the highest pH in water? So we know higher pH is more basic. So you have to see that in water, which of these will give the most OH minus ions. And if you want to see it in terms of H plus, which of this, which of these will give the least H plus ions? Okay. So here's the hint for this question. We have solved the past two questions on the same concept. So I don't think that you will have an issue for this particular thing, but that solves the question, right? So, and if you're always stuck, just remember that a solution is being provided to you. Okay. Now, at a given that the equilibrium constant has this value of 278 at a particular temperature, what will be the following constant of this particular reaction at that temperature? Okay, if you technically see, all right, you see this reaction R and see this reaction R dash. Okay, so a few things that I see. First one, that R dash is actually reverse of R. So R is reverse, then you got R dash, and then finally, let's say R double dash because that's it, and then you got R double dash by 2. So now we saw this. We saw these two things. Another thing that we saw is, if we just go back to the start of this when we were discussing everything, right? Yeah, over here. We saw that when you reverse the thing, you inverse the equilibrium constant, and whatever you are multiplying with, that increases to the power of it, right? So now if we see, if you found that logic, if that was clear to you, then there is nothing more left over here. Technically, that is what you have to do. So you reverse this, then you're taking the square root. So technically, you're just doing 1 by root k. That is 1 by root of 278. Okay. So then you just need to solve this particular thing and you will get this. Okay, which is close to 0.06. That is fine. Okay. So that would be 6. Now, just a vague thing on how they did it. So we know that if we take 100 divided by 278 into 100, what I did was I just divided it this into this. I made it by 100 because 1 by 278 would actually be a very small number. You can see that it is approximately this, right? So now what I am doing is I am just approximating this a bit to 275. Okay. Now if I just ignore this, and now this will become approximately 275. So whatever is the approximation of 100 by 275, both of these will actually go on 25 tables, right? That'll be 4, and that will be ones are 11. 4 by 11. Now whatever this is, somewhere around that only it will be. Now if we see, this will come around, let's say 0.44 something, right? Now you're dividing it, it will come out 0.4, the closest square to 44 is 6, 7 is 49. So 7. So it will lie between 0.6 and 0.7. Somewhere it'll lie over there in that range. Okay, so you have 0.6 to 0.7 middle of that particular part and dividing it by 10 yet. So again, your entire thing will be between 0.06 and 0.07 approximately. And the closest of your options in that range is your option C. Okay. So that is particularly how they even just got an idea of this with a rough calculation, because you don't have calculators allowed in your exam. So that is the thing. Okay. This is the same form of the equation. What we are doing is reversing, then dividing. So you have to not even calculate, you have to just tell what it's going to be. Now, which of these are least likely to act as a Lewis base and a Lewis acid? So now for this, you need to know what is a Lewis base and you need to know what is a Lewis acid. So a Lewis acid is basically an acid that accepts an electron. Okay. Lewis acid accepts an electron. And a Lewis base, it donates an electron. Okay, Lewis acid accepts an electron, Lewis base donates an electron. Now, which of these is least likely to act? Which of these will least likely donate an electron is what basically is. Now we know that BF3 is a Lewis. Uh, it will act as a Lewis acid and very likely act as a Lewis base, because we know that BF3 forms a basic 3 center 2 electron bonds, right? Similar to BH3. So there is no way that it can donate it. Question number 32, again, you have to again, they are asking literally the same thing. So just keeping the same thing in mind again. Now, this time they are asking Lewis acid. The question still remains same. Whichever is electron deficit will accept the Lewis acid, will accept the electrons, and that will make it a Lewis acid. And we know B2H6 has less electrons based on the structure that it follows. All right. Then, which of these molecules acts as a Lewis acid? Oops. Okay. So now basically you have to just see which of these are electron deficient, and when you finally find the particular atoms, sorry, which particular compounds that are electron deficit, you can just tag them as a Lewis acid. Okay. Next, the final question of the day, and that is a bit of a calculative question. So now what happens is, in this question they are telling equal volumes of three acids. One is pH 3, one is pH 4, and one is pH 5 is mixed in a vessel. What will be the hydronium ion concentration of each mixture? Now for the calculation part, let's keep this page open, but let's understand what's happening first. So initially you have a beaker, right? And that beaker you put in three acids. Let's say acid 1, acid 2, and acid 3. The pH of acid 1 is 3, the pH of acid 2 is 4, and the pH of acid 3 is 5. Okay. Finally, you mix it and you get a result solution. What they are telling is you have to basically see what is the concentration of H plus in this resulting solution. Okay. Now we know this formula, log 10. Okay. And this is our concentration minus, and that is going to be pH, concentration of H plus then. Okay. So if our pH is 3 technically, that means we have to get this. That means it is actually this. And if we see from this and this equivalent, this is my concentration of H plus. Right. So if I see for this acid, my concentration of H plus, let's write it with some other color. For this acid, my concentration of H plus is actually equal to 10 power minus 3. In this, my concentration will be 10 power minus 4, and this, my concentration will be 10 power minus 5. Okay. Now, If we are mixing equal volumes, then what is going to happen? We are going to basically get 1 liter, 1 liter, 1 liter of each acid, let's say, and we are going to get 3 liters, right? So 1V, 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 and 3. That's it. Technically, what we are doing now is basic calculations. So what is happening is we are seeing M1 V1 plus M2 V2 plus M3 V3 should be equal to MV. Now, because all are equal, I can say V times M1 plus M2 plus M3 will give me M, and you're telling 3V will be left over here, right? So V gets V, and now your final M will actually be equal to M1 plus M2 plus M3 divided by 3. Okay. What we are basically doing is whatever we just saw in the titrations part. Remember, we had just recently seen this equation that we solved for a particular question. M1 V1 minus M2 V2 gives rise to MV. So this was an acid and this was a base, and they were reacting. Here we have three acids. So those three acids, their equivalents will add up to give me the final equivalent, right? Now what they are telling, they have told equal volumes. Equal volumes means you are selling V1 is equal to V2 is equal to V3, and that, let's say, is equal to V. And keeping that in mind, what you're doing is you're adding V, then you're adding V, then you're adding V, and finally in the whole container you will be left with 3V, right? Now, considering that you have those three V's over there already, and you have this thing, I can take V common, right? Let me just say. So what I did was I took M1 V1 from the A1 acid, okay? And then I took M2 V2 from A2 acid, and then I took M3 V3 from my A3 acid. I mixed them, and I got some final MV. Now V1 was equal to V2 was equal to V3. So I can take V common because, okay, M1V plus M2V plus M3V. Now because you're adding three equal volumes, this V final will actually be equal to 3V, right? So 3MV. Now what I can do is I can take V common and I can cancel V out, right? So M1 plus M2 plus M3 by 3 will be my final M, right? Now we got this, we got this, we got this. We have to just divide it by 3. And this is what this part of the calculation does. And now whatever this part of the calculation comes up to, you can just solve it and you can get your closest answer. And with that, you can just find your particular option. Okay. So with that, we have technically completed the questions for equilibrium, both chemical and ionic. So a few things that you need to keep in mind over here. First one, we have focused, they have asked a lot of questions around constant and its basics. And its basics, that means what will happen when you reverse it, what will happen when you like increase the moles, what will happen at endothermic and exothermic situations. You have to see those things. The next most asked question was around the concept of pH in ionic equilibrium and POH. And always, whenever you are trying to solve these questions in a mixture of things, right? Whenever you go in mixtures, just go into the concepts of equivalence. Okay, equivalence, the M1V1 plus M2V2 or M minus M2V2 if it is a acid base combination, base base or acid acid M1V1. Basic logic is that equivalence should be equal in both the types. Okay, and another basic most generally asked question was around Gibbs energy. Okay, so we saw that these three particular topics were coming a lot, were asked pretty frequently in your exams. So keep these three in mind. And other than that, please be revising every single thing one by one. All right. There were a few questions on Bronsted and Lewis acids also. So just keep your base fundamentals strong on this. So that was it for this particular chapter, guys. And thank you all for attending this class. And we will see you all in the next one. All right. Thank you, everyone.